Hello and welcome to a new video in a course on linear algebra. In the previous video, we defined subspaces, we defined the notion of subspaces, and we gave two equivalent definitions and we proved the equivalency of the definitions. However, we ran out of time and we haven't had the chance to give some examples. So in this video, I'll be giving some examples of subspaces, and in doing so, I'll be giving you a handful number of examples of vector spaces, because at the end of the day, a subspace is just a vector space, right? But it's just a subset of a bigger vector space. So you will have a lot of examples of vector spaces to keep in mind. And other than that, there's a property of subspaces that I'd like to go over. And I promise this is the last video on this chapter, and in the next video we'll be covering linear transformations and so on. So the next video is going to be a new chapter. Anyways, so let me remind you real quick of what the two definitions of subspaces were. So definition 1, a subset S of a vector space V is a subspace so V is a vector space with two operations. S is called a subspace if first of all S is not empty. Second, S, when equipped with the addition and scalar multiplication of V, like the same operations, is a vector space. So this definition 1, we said that though it kind of gives you the main idea of what a subspace is, when it comes to practice, when it comes to checking or proving that something is or is not a subspace, or when it comes to proving something is a vector space in general, because I remind you, I gave you this trick that to prove something is a vector space, it's enough to prove that it's a subspace of a bigger vector space, right? So so there is this other interesting definition which is equivalent to the above, which I advise you to use because it's kind of shorter to remember and to check. So a subset of a vector space V with two operations is a subspace of V. So here I should have mentioned of V if, first of all, it's not empty. Second, it's closed under addition and scalar multiplication. So I should mention here before we start giving some examples that some people, some textbooks, some professors usually they usually replace the condition 1 with the fact that 0 should be in the set, the 0 of the vector space, but it is equivalent just as I showed you in the last video. So it's enough to check that there is at least one element in the vector space, one vector in the set, in the set S. So this is what we got, this is what we have, and we said that we're going to be using definition 2 because it's easier to check, and it's easier to check something closed under addition and scalar multiplication instead of checking that it's a vector space. So when giving, so I'll be giving some examples, some of which I'll be orally proving why they are a vector space, and others I'll be writing sketches, and for others I'll be writing sketches or complete proofs. So let us see. So the first example of a vector space, so given a vector space V itself, like the vector space V, if you consider it as a subset of itself, then V itself is a subspace of V. Well, this is clear, right? Because so there are two ways to see it. Let's see it directly from definition 1. Well, V is a vector space, it's not empty, and thus this is not empty. And well, why is the V not empty, by the way? Because the 0 is there, right? This is important to keep in mind. A vector space is never empty because we always have an additive identity. We always have at least 0 there, right? So V is a vector space, hence it's not empty, and it is itself a vector space, and hence it's a subspace, right? So this is a check by definition 1. You can always check definition 2 because, of course, it's closed under addition and scalar multiplication, right? The trivial subspace, this is called the trivial subspace. 0 is itself a subspace of the vector space V. So this we discussed in the last video, so I refer you to the last video to see this. So let us do the next example. So the next example is the set of all vectors in R cubed where we take the third component to be 0. Okay, so let us write here a few things because it's important, right? So to begin with, so we want to prove that omega is a subspace of R cubed. This is what we want to prove, right? And I should mention here, we'll prove that it's a proper subspace. I'm gonna justify what I mean by that. So let us prove using definition 2. Let's prove that using definition 2. So the first thing we check, omega is not empty. Well, of course it's not, because 0, 0, 0 is an R cubed, and it has the property that the third component is 0, and hence it's an omega, right? So it has an element, it's not empty. So the second property that we need to check is that it's closed under addition and the scalar multiplication. Well, also it is, because if you take x1, so let me just say, for every x1, x2, 0, comma, x1, x2, prime, prime, 0, in omega, if you take any two elements in omega, right, and let's say for every real number R, right, first of all, under addition, it's clear that if you add these two, what do you get? Well, you get x1 plus x1 prime, x2 plus x2 prime, third component is still 0, and thus this is still an omega. Clear enough, right? So the second check is that want to check closure under scalar multiplication. Well, if you hit a real number by this vector, well, what's happened is that this is rx1, rx2, and thus this is still an omega. So also closure under scalar multiplication is evident, and this proves that omega is a subspace of R cubed by what? By definition 2. So here's an important thing. Instead of you, say I asked you a different question. Say I asked you that prove omega is a vector space. Well, there are two ways to do this. One way is to go ahead and check all the axioms of defining the vector space, which are around 10 or 12, I don't know. So these are a lot to check, right? So this is one way. The other way is to notice that omega is a subset of R cubed. But R cubed is something that we already proved is a vector space, and thus it's enough to prove that omega is a subspace of R cubed, because a subspace is literally a vector space, right? So it's enough to prove that omega is a subspace of R cubed, which means it's enough to check these two properties, right? How easy, right? So so yeah, I mean, take it easy. So this is what we have, right? I just want to mention here that it's a proper because, why is it proper? By proper, I mean that a proper subset, so omega, we write omega is a proper, and we write here it's not equal to R cubed. So there is an element in R cubed that's not an omega. Well, of course there is. Consider 0, 0, 1. This is an R cubed, right? But this is not an omega. This is not an omega, right? Well, because the third component is not 0, and thus, since the third component is not 0, it's not an omega, but it's already an R cubed. So, you know, it's a proper subset. It's a proper subset, and hence it's a proper subspace. So yeah, so this is it, right? So the next thing we need to check is that, or the next example I want to give you, is that the set of continuous differentiable functions. So if you consider the functions that are continuous, differentiable, and whose derivative is continuous, then this set is first of all a subset of the space of continuous functions, because I mean differentiable functions are continuous, so every function that is differentiable is continuous, which means C1 of R is contained in C of R. So this is clear. So this is a subset, right? And I guess we proved in a previous video that this is a vector space. We proved that this is a vector space in a previous video. So to check that this is a subspace, well, it's not empty. Why is it not empty? Well, because of course there is a differentiable function. Of course you can name a differentiable function, right? So C1 of R, let's do this. I wasn't planning to do this, but maybe it's an easy thing to do, so let's do it real quick. So C1 of R is not empty. Why? Because f of x equal to x, this as a function, let's define it from R to R. This is a differentiable function, right? So f is in C1 of R, so it's not empty. Second, you want to check closure under addition and scalar multiplication, but we know that if f, g are in C1 of R and R is a real number, then f plus g and R times f are differentiable with continuous derivative. In other words, you know from your calculus course that if you add differentiable functions, if you add two differentiable functions whose derivative is continuous, and thus you still get a differentiable function whose derivative is continuous. No surprise. And similarly, if you multiply that function by a constant. So I went over this real quick because it's an easy example, right? I want to save time for some harder examples where we go over these in details, right? So this example is gonna show up over and over again. This is why I want to cover it, because it's related to a concept that we'll be covering later on, and it's called spans of vectors, like the concept of a span of a vector, or a span of a set of vectors, and we're gonna be seeing this later on in the course. But I wanna prove to you here that if you start with the vector space R2, what I want to prove to you here is that if you start with the vector space R2, if you start with this vector space, right? You know, I remind you, R2 is the set of all tuples where these are real numbers, right? This is R2, this is by definition what R2 is. Now what we're gonna do is that we're gonna fix a vector. So we're gonna fix a vector in R2. We're gonna choose a vector, for example, 1, 1. We choose a vector, right? Choose a vector with components x1 and x2. And what we're gonna do is that we're gonna multiply that vector by all the real numbers and collect these elements, right? Because, you know, R2 is a vector space, and thus is a vector space if we equip it with the element-wise addition and scalar multiplication. And we defined R times V. In this case, if V is R, in this case, if V is defined as such, it's going to be Rx1, Rx2. And what we're going to do is that we're going to run over R, and we're going to collect all of these vectors, right? I guess I'll slow down now because I don't want to get anyone tortured by this. So So again, omega is the set of all vectors of the form rx1, rx2 as r runs over the real numbers. So this is what we're taking. We fixed v, and we're hitting v by all the real numbers, and we're collecting all of these elements. So this is the set of all r dot v, where r is a real number, and we fix v in R2. And the claim is that omega or W is a subspace of R cubed, excuse me, R2. So why is that? Why is omega a subspace of R2? Remember, by definition 2, we have to check two things. First, we have to check that it's non-empty, and second, we have to check that it's closed under addition and scalar multiplication. So let us do that. Well, first of all, omega is not empty. Why is that? Because 1 dot v, right, which is v, right, this is in omega, right? Because omega is the set of all vectors of the form real number times v. Well, you can take the vector 1 dot v, right, which is v. V is in omega, right? This is no surprise. So this vector is in omega, right? Second, which means omega is not empty. Second, why is it closed under addition and scalar multiplication? So let's take any two vectors in omega and check that they're gonna, if we add them, they're gonna still be in omega. So for every r1v and r2v, remember, vectors in omega takes the form a real number times v. Thus, if you want to take two vectors, it's going to be r1v, like a real number times v, and another real number times v. So let's take these in omega, and for every real number r, because we're going to check scalar multiplication. So first of all, why is it closed under addition? Because if you take r1v plus r2v, then by the property of distributivity in the vector space, we have r1, this is equal to r1 plus r2 dot v. But this is in r, this is a real number, and we're multiplying it by v, thus it takes this form, and thus this is in omega. Surprise, surprise. And the second thing we need to check is closure under scalar multiplication. And this is easy also, because if you take r and you dot this with r1 times v, right, this is any vector that we started with. If you expand this, but if you rewrite this using the distributivity in the vector space, you can rewrite this as r times r1 as real numbers times v. But multiplying two real numbers still give a real number, and thus this takes the form of a real number times v, and thus this whole thing is in omega. So that is it. We just proved that omega is a subspace of R2, right? So this subspace is called the subspace spanned by V, right? We're gonna be defining this later, but I'm just trying to throw some important terms here. Please, these examples that we went over, please make sure that you understand these well, and you understand any tricks that you've seen when we were proving that these are vector spaces. Keep these examples in mind, because remember, one very important trick when trying to prove something is a vector space is to see if it's a subset of a bigger vector space. Because if it's a subset of a bigger vector space, then what you can do is that you can just prove that that set is a subspace. And we've seen that it's easy to prove something is a subspace. We only check three properties. Thus, these examples are important for you to see later on if you've encountered a problem where you're asked to prove something is a vector space, well, you now know that you have a bunch of examples of vector spaces, and you need to check, and your first check should be whether or not this set is a subspace, is a subset of some of the vector spaces that you know. Anyways, so I just want to prove one important property of subspaces, because this is something that's going to show up later. Here's the property. The property says that if you take any collection of subspaces, so if you fix a vector space V, right, and you take any collection of subspaces, right, you take a collection of subspaces, take many subspaces, and take their intersection. If you take many subspaces and take their intersection, then that intersection is itself a subspace, right? So let me state this. Well, it's stated. Let me prove it. So let me just write here the proof of proposition 4.2. Okay. So what the proposition is saying again, let V be a vector space, and let omega sub alpha as alpha run over some indexing set I be a collection of subspaces omega alpha of V. So omega alpha are all subspaces. So we're indexing omega alphas by alpha, whatever. So we want to prove that the intersection of omega sub alpha as alpha runs over I is a subspace of V. How nice, right? So let's call this omega, because we want to reference this. And what does it take to prove a subset of V, a vectors, to be a subspace of V? What does it take to prove a subset of V is a vector space, is a subspace of V? Well, you want to prove that it's not empty and it's closed under addition and scalar multiplication. Well, these are easy to check, so let's check these. First of all, why is it non-empty? Well, it's non-empty because each omega alpha is a vector space, because each omega alpha is a subspace, hence each omega alpha is a vector space. So 0 is an omega alpha for every alpha. So since these are subspaces of the same vector space, they all have the same 0, and 0 is in all of them. But since 0 is in all of them, this means that 0 is in the intersection of all of them. This is the definition of intersection, right? But since 0 is in the intersection, which is omega, right, which is W, then W is not empty. It has an element, right? Alright, and the next thing that we need to check is closure under addition and scalar multiplication. So let us do that. So let us take omega 1, omega 2 in W and a real number R. So let these be any vectors and R be any real number, right? So let's prove closure under addition. So we started with omega 1 and omega 2, and we want to show that their sum is in W, right? So omega 1 is in W, and omega 2 is in W. But W is the intersection of all the omegas. And what does it mean for something to be in the intersection of a bunch of sets? Well, it means that omega 1 is in W alpha for every alpha, and omega 2 is in W alpha for every alpha. This is by set theory, right? And thus, since both of these are there, we know that omega 1 plus omega 2 is in omega alpha for every alpha. And why is that? Let me just say here, let me stress here, why is that? So omega 1 is in is in W alpha for every alpha, and omega 2 is in W alpha for every alpha. Each W alpha, this is because each W alpha is a vector space, because each W alpha is a subspace. Since each W alpha is a subspace, hence it's a vector space, and thus it's closed under addition. Like every vector space is closed under addition, right? So if we add omega 1 and omega 2, we still get them in W alpha for every alpha. But again, this literally means that they're in the intersection of all the omega alphas by set theory, because we have the for every here, right? So this is by set theory, but the intersection is what we call W. Okay, so this is closure under addition, and similarly closure under scalar multiplication is easy to check. You start with omega 1 in W and a real number R, and you say you want to prove that R dot omega 1 is in W. So this is what we want, but omega 1 is in W, which is the intersection of all the omega alphas, which means that omega 1 is in W alpha for every alpha, because this is the definition of intersection. And because each omega alpha or each W alpha is a vector space, right? Hence closed under scalar multiplication, then R dot omega 1, right, is in omega alpha for every alpha. Why is that? Because again, omega alpha, W alpha is a vector space, and hence if we scale multiply the vector omega 1, which was in omega alpha, in W alpha, we get still a vector in W alpha. And thus by definition of set theory of intersection, since this is for every, we have that R dot omega 1 is in the intersection of all the W alphas. And that's it. We just proved closure under scalar multiplication, and this proves that this is a subspace. That's it. I'm gonna leave these two examples for you to check, to verify as an exercises why these are not subspaces. So you need to check whether they you need to check what property. Like we have two properties. Either either it should, like a subspace should be non-empty and should be closed under addition and scalar multiplication. So check which of these properties fails for these two sets, which makes them actually I stated for you the reason. So just check that. Give yourself a counter example and check that these are not subspaces, right? So give counter examples to yourself to see that these are in fact not subspaces.